Thank you for staying here with me. After the great awarded talk by Brian. So thank you for still being here with me and the other speakers. So I'm introducing my work. It's called CatchTartan, representing and summarizing dynamic multi-contextual behaviors. It's a joint work with Professor Han and Professor Christos. So I think you want to use like Google search to know what is Tartan, but I can let you understand that Tartan is it's a big story, long story. I visited CMU in 2012 to 2013, and we visited Christos, and I watched lots of Tartan's game there because every sports team in CMU were named as Tartans. So I watched football, soccer, and men's, women's. Watched a lot of games, but most of them, yes, we lost most of them, really, most of them. So I think I should write something to memorize such experience since I was very frustrated. So after, this year I read this paper about Tartan, okay? But it's a joke. So Tartan, I want to use Tartan to summarize and represent the behavior. So let me introduce what is behavior and why you want to do this, okay? Behavior, if you search on Wikipedia, they said it's interactions made by individuals, by our human beings with themselves, as well as the environment. The environment may have multiple contextual information. Let's say, here are two examples. One is tweets, one is publishing paper behavior. So it's not just the user and the author and the paper title. It's like your co-authors, the conference that you submitted to, right? Your affiliations, for tweets, it's not just the user and the tweet. We also have the hashtag. We also have the topic. If it's a geo-tagged tweet, we have the location and the time as well. So there are many contextual factors in these tweets, in these behaviors. So why we want to do behavior modeling is, let's say, what we can discover from the rich knowledge behavior data. If we are given every phone call, every message between the military leaders, between the scientists, maybe we can uncover lots of mysteries, right? So it's very valuable, but we know that it's undoable today because we don't have the phone calls between Hitler and other presidents. But we can do that today, right? We have a large online environment. We can collect lots of online behavior data. For example, I have showed two examples, right? Even for a researcher in universities as me, as anybody, so we can collect the tweets from Twitter. We can collect the papers from DBLP. Actually, just download it. It's very easy. So I think it's the first time that we can get insights of the human behaviors in our society, especially when there are many industry companies. They collect lots of, they have sensors for the society, so we can collect lots of data, right? So we can understand it. To do behavior modeling, there are majorly like 5 steps. I think the first is we want to represent the data into math, right? The second thing is we want to observe some interesting patterns. For example, the research trends when we have the DBLP data, the events when we have the Twitter data. So we want to summarize the data, the large-scale data, into some interesting summaries. And the third would be understanding these summaries, understand the observations. For example, we can observe some influence or intentions, such kind of patterns. For example, intention of the thrusters, right? So the fourth step is to predict what will happen in the future. And we are trying to, for the companies, especially for companies, we want to trying to build some systems that to intervene in their behaviors. For example, we build recommender systems, we build fraud detection systems. So that's like 5 steps. But here, for this work, we want to focus on the first 2 steps, which is representing and summarizing the behaviors. Okay. So the problem is like this. So given the behavior data, for example, the DBLP data, so we have it's a paper, right? Okay, it has the time, the year, and the co-authors, the keywords in the title, the conference. So we want to return some behavior summaries, which has the research trends of the research committee. For example, from 1997 to 2012, this is a shot of the output in our method. So we can see the first trend is the IR trend, which means there are 76 leading authors, researchers from 2003 to 2007, these 5 years. They research for the published papers about the information retrieval on 7 conferences, including SIG-IR, VLDB. So this has, we call it 4 dimensions or 4 contextual factors, including authors, venues, keywords, as well as the papers that is cited. And the second trend could be the venue and keyword, which is about reinforcement learning, about machine learning during the 5 years from 1997 to 2002. But you can see that maybe at that time, there's no such leading authors. Maybe every researcher wants to publish paper about the reinforcement learning, and they just can publish like 1 or 2 papers. Okay, there's no leading authors during these 5 years. So when we want to summarize this research trend, we can have just the 2 dimensions, including the venue, the conference, as well as the keywords. But maybe we don't see that they all cite the same set of papers. We didn't see that there are some leading authors. So if we want to return such kind of summaries, we have to know how to represent the behaviors. Okay, so the behaviors have very important 2 characteristics. One is dynamic, one is multi-contextual. For dynamic means that it has time, right? It should be located in a time slice. Let's say here is a tweet, so it has a time. And for the context, which means that like we call it maybe environment something. So we know there are keywords, there are like words or phrases in the tweets, as well as the hashtags, as well as the locations. But for all these dimensions, the user dimension, the location dimension, the phrase dimension, the value could be just 1 guaranteed value, for example, for user, right? Why 1 tweet can just have 1 user, right? So, but for the location or for the hashtag, maybe there's empty set for this dimension. No hashtag, no location. And there could be multiple values for the phrase. A tweet can have multiple phrases, right? Definitely. So also, it happens for papers, right? So we can have multiple authors, multiple keywords, right? Multiple papers to cite. So how to define a summary of the behavior is we say, for the dynamic thing, we want to give a summary which takes a set of consecutive time slices, including multiple contexts, which is a set of dimensions, like a user or maybe author or conference, and a set of dimension values in each dimension. Okay, so that's the definition of the summary. Let's say to deal with the multidimensional information, a very powerful tool is tensor. So tensor is an n-dimensional matrix. We say matrix has 2 dimensions, okay? And tensor has n dimensions. It extends the dimension into n, okay? But tensor, it's very powerful. It can deal with, let's take 4-dimensional data. For example, we have a phone call data, the caller, the callee, location of the caller, location of the callee. So we have 4 dimensions. We can use tensor to represent it. Every cell is the phone call, which says this caller to this callee from these 2 locations, between these 2 locations. But this tensor requires 1 value, exactly 1 value on each dimension. You can just have 1 caller, 1 callee, 1 location for this caller, 1 location for this callee. But for these behaviors, many other types of behaviors, like papers, like the tweets, maybe we have multiple values. We have empty values for some dimension, right? So how can we represent the empty value of each dimension, represent multiple value for each dimension in tensor? It's impossible, right? We cannot argue, we cannot require every tweet to have just 1 phrase, okay? And when we do the summarization, we have to consider about the dynamics. So if we want to represent the temporal values, the time information in a tensor, it cannot be consecutive. We just lost the consecutive information, the temporal information, actually. So for when we do summarization, we want to look for the block, the dense block in a tensor, okay? So it's a set of time stamps instead of consecutive time slices. So that's also another challenge, another problem. So that's how we try to propose a novel representation. We call it 2-level matrix to represent the behavior. So they have the tensor extends the dimensions from 2 to n so that they can represent multi-dimensional information. But here we have multi-contextual information. So we say we can extend the columns. Well, the columns could be extended to 2 levels. The first level is the dimensional type. For example, the user dimension, phrase dimension, URL dimension. And for the values, for example, the user part, we say every column is the user value. Okay, every column for the phrase level, phrase dimension is the phrase value. So now let's take like the rows. Okay, we can put it like the consecutive time slices, the year 2002, 2003 into time slices, and in each time slice we have several papers or several tweets. And a row is a tweet, a row is the behavior. Okay, and let's see whether we can do this, do the representation for every behavior, every paper, every tweet in this 2-level matrix. So if a row is the paper or is a tweet, we have 1 user, okay, 1, check, and the other will be empty, okay? And we have 2 phrases, so 2 ones there. The other columns will be empty. And we have 1 URL, no problem. And we have no location, no hashtag. Okay, let's leave it as empty. That's okay, no problem. So we can use this 2-level matrix to represent every tweet, every behavior. Okay? So now comes the question is, what is a summary? So in a tensor, the summary could be a dense block, which means that a set of users, a set of hashtags, a set of phrases come into a dense block. But here, for the two-level matrix, we say a summary may have different sets of dimensions. For example, in the research trends, we know that it could have 4 dimensions, like the authors, the venues. It can just have the venues without leading authors. Okay? So maybe we want to represent the summary with a set of dimensions. So you can see here there are 2 summaries. One is block, one is purple. And the block one will take 3 dimensions, the user, phrase, and the URL from the 5 dimensions. Okay, all the dimensions. Just take 3. And we take a set of values from each dimension, the user set, the phrase set, and the URL set. Okay, and we also take a set of consecutive time slices and a set of behaviors for each slice. Okay, so then we took like this shape. We realized that I just realized it's a tartan, exactly CMU tartans. Okay, so then I think I may write a paper and to memorize my experience. If you still remember that we lost the game. So the definition of this problem is given the behavior data, we formalize it into a two-level matrix. And how can we find the summaries of the tartans? Okay, and we employ a lossless encoding scheme, which is based on the MDL principle. It's minimum description length. So the general philosophy is we want to give a principal score based on information theory to know the importance or significance, or we call it metric, for the tartan. Okay, for the tartan. If it has a high metric value, we say, okay, it's a good tartan. Okay, so we can give a principal scoring function for the set of dimensions, the set of values for the tartan. And the philosophy is whether we can save more bits when we represent the tartan from the data. Okay? So we know that the two-level matrix could be very sparse. So when we represent the sparse matrix with some digits, with some bits actually, so we say we have to encode every position of the 1 entries. Well, it's very sparse. And we know that the tartan could be somehow dense because it's significant in the data, right? So we say tartan is denser than other entries. Well, the noise, the rest of the data is much sparser, right? So we can save lots of bits when we represent it. So you can see here is the objective function of the encoding cost that you want to try to maximize. Okay, the first term is the number of digits we have to use to represent the data. And the second term is the number of digits, the bits that we want to use to represent the tartan. Okay, the last one is the number of the bits we have to use to represent the noise. Okay, since the tartan is denser than the data, the noise is sparser than the data, so we can save somehow a lot of bits by representing the tartan from the data. Okay, we try to maximize it. So to represent the tartan, it has a different encoding cost function because we can, since it's denser, so we can just encode the dimensions, the values, the slices, and the behaviors. So we can see for encoding cost function of the tartan, we have 5 elements. One is how to encode the dimensions. So we can see here is a blue tartan. It has 2 dimensions, right? From the 3 all. I mean, the dimension vector will be 1, 1, 0. So we're trying to encode this vector to know what the dimensions we have selected in this tartan. Okay? So we can encode the dimensions. We encode the values from the blue parts, the blue columns from each dimension. We can encode every time slices in the tartan, every behavior in the tartan, and then we can encode the entries. Okay? With these 5 elements, we have the result for the function to encode the tartan. Now we have the metric function, we have the scoring function. So how can we find the best tartan? So we developed a greedy search algorithm which trying to update the set of the behaviors. So we fix the columns. Okay. Now we try to update the tartan with to see whether we want to put more or fewer rows in the tartan. Okay. So we consider the red parts. So we fix the columns, consider the rows. We fix the rows, consider the columns. And we do it iteratively, as well as to see whether we want to put more time slices and other dimensions in the tartan. And the principle is we have a scoring function, right? So, and we know that for this, the time complexity is quasi-linear to the data size, which is good. So here are some results for the DBLP things. We have shown that there are several research communities or trends. I can show another thing is on the second row. You can see there's a tartan, actually. It has 3 dimensions. The leading authors are Professor Han, Professor Xifeng Yan, 6 authors, published 22 papers in 7 years, 2004 to 2010. All cite the same paper, which is frequent subgraph discovery. And all these papers were published in SIG mode. So this is very important about subgraph mining research trend, which was caught or represented as a tartan and caught by our algorithm called CatchTartan. Okay? And another experience is on the data set, Twitter data set from about the Super Bowl. So we collect all this data. And we can see when we report the tartans, we can see the first thing is about the score prediction event. So the most important dimension, actually the first tartan has just 1 dimension, which is the freeze dimension, about score prediction, okay? But during the, let's say the fourth tartan, which have 3 dimensions, the freeze, the user, URL, which is happened during the halftime show, where there are some advertisement campaigns, and the advertisers try to promote their URLs as well as the halftime show phrases, which forming a dense tartan as the number 4th tartan with 600 tweets. So this is what we found. We can say it's like events, sub-events during the Super Bowl, including the score prediction, including the first quarter, halftime show, second quarter, as well as the last of the game, the game over thing and the congratulations thing. So that's an interesting summary for the Super Bowl event. And all this was done automatically, right? We have the principal scoring function. We don't have to set up any parameters. And so we know that it's hard to evaluate the tartan by human labeling. We cannot label tartans. We cannot label even blocks. We can just label for data points, right? So here we did the same thing, similar things as the Froda. So we inject the tartans into a synthetic data. And we can control 8 parameters, 5 for tartan distribution, including the number of the time slices, number of the dimensions, as well as the densities and the noise, and the data distribution for with 3 parameters. Okay, and I'm sorry, there are many figures to test about the efficiency and the effectiveness. If you take the paper, it's better. But we know we just demonstrate that our method it's course linear to the data set, so it's very efficient, and the performance is quite good. We can catch the injected tartans. Okay, so here is the summary. So the most significant thing in this paper, in this work, is we propose a novel representation for the behaviors, so that you can do behavior modeling from the representation summarization to other things like understanding it, predicting it. So we propose 2-level metrics, which can represent all the behaviors, including tweets and papers, all the behaviors which have dynamic and multi-contextual characteristics, which have multiple values in several dimensions, not just 1 value. Well, the tensor requires 1 value in each dimension, right? So we have a new representation, and based on this representation on the behavior, we propose a new summary definition for behavior summary, which is a tartan. It's not a dense block in tensor anymore. So under the tartan, then we propose a summarization algorithm. It's called CatchTartan that can give a principled scoring function based on MDL principle, and it's parameter free and it's scalable. It's course linear to the data size to catch all the tartans and report as what we saw in the visualization on the events of the tweets and as well as the research trends in the DBLP data. And we do experiments to demonstrate the effectiveness, discovery, and efficiency. So thank you all. And I still want to say go Tartans. Yeah.
OK, we have time for a few questions. So for anybody sitting a little far, you should come down here on both sides. If you're sitting in the middle, you can use this one. OK. So any questions? Yes, go ahead.
Hi, very interesting work. Have you also thought about using some item set-based representation instead of the 2-level matrix?
Well, that's a very good question. So for item sets, or especially when yesterday we did the poster session, so everybody asked, maybe we can do some like clustering, right? Co-clustering, like such kind of thing. So we will talk about the features. Since we have the data points, which could be the behaviors, that's OK. But for every feature, actually here we have dimensions. I mean, all these features may have different feature types. All we call here is dimension types, including users, phrases, and our URLs. You have, when you do the summary, you have to give a principal scoring function to know whether you want to include this set of dimensions in the tartan or in the summary, right? So for the cool clustering or for the maybe item set, frequent item set mining, it's hard to know how to score the set of the meaningful dimensions as well as the values. So I think when we consider this, we may call it multiple types, or it's like heterogeneous in the data, this tartan will be better, I think.
Okay,
thank you.
Thank you.
Okay, so any more questions? Right, go ahead. You can use this one.
Thank you for the talk. I think I see the advantage of tartan in the multi-contextual information encoding, but how about the dynamics? I mean, from what you talk, I see you are putting all these timestamps together and for the inference of the tartan. But are we modeling the evolving nature of the informations, of the interactions, the behaviors over time?
We didn't model the moving natures, but we say that for tensor representation, it cannot take care of the consecutive thing. I mean, it's not like temporal dynamics. So here for us, we say, okay, for this updating, when we update the sets of the time slices in the tartan, we just consider the neighbor time slices. I mean, the last previous one or the next one. So we want to know whether we want to include more time slices or fewer time slices, which can be a consecutive setting for the tartan.
Yeah.
So it's
I mean, I'm looking for ways to characterize this evolving nature of the stuffs, and explicitly.
Well, that's a very good question. So that will be. So I think that will be the third step of the behavior modeling. Actually, we want trying to understand the patterns. So you say you want to model the dynamic structure, right? So here we are just trying to demonstrate, show your observation in the data. We give the trends, but we didn't model the structure actually. I mean the dynamic structure actually. So we want to mine the structure from data to show you some interesting observation. But based on this observation, maybe you can find something like, it's not easy for the recommender system to know where is the influence until they realize there are some influence cases in the data. So here we show some trending cases. We showed some tartan cases so that you can see, okay, maybe there are some dynamic structure, and then we do understanding, we do prediction, we do intervening the behaviors by building some systems, which is fantastically cool, I think.
Thank you.
Thank you.
Thank you. We have time for one more question, if there's any. Okay. So if we do not have question, let's thank the speaker again.